So I first want to thank everyone who's in this room on day 3, the earliest talk, 9 a.m. I'm super impressed by all of you. So my name is Logan. I go by _Logan McDonald on Twitter, and you can feel free to tweet at me during and after this talk. I am a site reliability engineer at BuzzFeed, where I work on our platform, and I concentrate on the security and usability of that platform. This illustration of me was made by Emily Griffin, who is Emily with Curls on Twitter. All the illustrations in this talk are by her. That is me, even though my avatar person has not caught up to my real-life hairstyle. So I want to get started with a story. So I studied economics and math in college, and I wrote my senior thesis on a particular field in economics called behavioral economics. Behavioral econ marries insights from studying human behavior with the statistical tools from economics. It turned out that I was more interested in writing the code to program regressions than I was in the regressions themselves. So when I graduated, I pursued a career in software, but my interest in behavioral econ really remained. So flash forward to my first week on the job as a baby SRE. There was an incident with our search system, and I got to witness my very first outage. I'll never forget, and maybe you've had the same experience, of staring at a plethora of graphs and logs in front of me with reds and oranges and only the occasional green, and trying to make heads or tails of it with this deep sense of urgency as I watched Slack chatter go by. I was standing near a senior engineer on our team, and I was watching his eyes fly over the same information. And suddenly, he just stops and says out loud, "Open file descriptors." And then he starts quickly typing, and minutes later, our system was green again. I was amazed, but to be honest, completely horrified by this wizardry. And I panicked that first week. I wanted to be a contributing member of my team as fast as possible, but I didn't know if I was ever going to get to that point. But then I recognized something in what he had done, and that's expert intuition. But I had the benefit that not a lot of other junior engineers or SREs have in that moment. After my anxiety had subsided because of my background in behavioral econ, I realized something else. Expert intuition is not magic. Expert intuition is achievable. So today, I want to talk to you about the journey that followed that realization and the tools I have used to overcome my fear of incidents. I also want to clarify that these tools not only helped me when I was first starting out, but they've helped me onboard to new systems throughout my career as well. I love this review that John Allspaw gives for his favorite world-class monitoring system. He says that it's one of the most powerful, context-sensitive, incredibly adaptive, anomaly-detecting, and responding agents in the world. And here he's talking about the human mind. One day, we may design tools that are more powerful, but until then, we can greatly benefit by improving our memories and optimizing our learning processes. So let's get started. I've broken this talk into 4 phases I went through using learning and behavioral science tools to improve my memory, and thus my ability to respond to incidents in my job as an SRE. The first category is preparation. When I took that first job as an SRE, I had a vague understanding of the field. I had previously interned at a company called Chef Software, where I got a good introduction to site reliability engineering and DevOps concepts, but actually working as an SRE and responding to incidents was new to me. So I set out with a question, what do I have to learn? And that's when I discovered something about the nature of our field. Site reliability engineering for complex systems often requires a vast amount of experience with a vast array of tools. So if you research what you need to know to become an SRE, you might find people saying, learn about the major cloud providers, but which one? You might hear people say, learn continuous integration tools, learn terminal skills, learn about logging, learn about security and networking protocols, and on, which left me feeling very lost and overwhelmed, a lot like this. And that's where my first tool in learning science comes to my aid, and that's the idea that problem solving is easier with constraints. In math and economics, we often deal with CSPs, or constraint satisfaction problems. These problems are mathematical questions that are defined by a set of objects whose state must satisfy certain limitations or constraints. And these become useful in our cognitive toolkit as well in an area of studies cognitive scientists call constraint theory. In constraint theory, cognitive scientists posit that when we constrain our conceptual combinations, we open our brains up to a smaller set of possibilities. So say that you are tasked with designing a room. You'll probably want to start by asking questions instead of jumping into the design. Your first question is probably going to be, well, how big is this room? And then, what needs to fit in it? This starts to constrain the infinite possibilities of your design. This is exactly what I needed to do when starting to work in a new and unfamiliar area. I often ask, okay, what do I need to fit in this room? So, for example, when I was learning SRE, I started my journey, as a lot of us do, with a very helpful guidebook, the Google SRE Handbook. In section 3 on practices, there is a helpful model called the Dickerson hierarchy of site reliability, named after Mikey Dickerson, who worked at Google. I found this to be a really helpful way of constraining what I needed to learn first. Because monitoring was at the base, I decided to tackle that. I brought this hierarchy to my manager and asked if I could be involved in building out our next generation monitoring system for our team. And I could have started anywhere when learning about SRE, but intentionally choosing an area of concentration was hugely helpful and bred a lot of creative freedom. So now that I had constrained my path for learning, where should I start? Could I jump in, building out the metrics pipeline? Which softwares should I use? This system says there's the benefits to tagging metrics in a certain way, but what exactly does that mean? Well, it turns out that there are some helpful models of hierarchies of learning that provide us places where we can start. My favorite is Robert Gagné's hierarchy for learning. So this hierarchy starts with signal learning and stimulus response learning. This means lots of trial and error before making associations and finally solving problems. This led me to start with proofs of concepts with different systems rather than pure research. And it was beneficial to me in those early days to start building as fast as possible. So I want to highlight the second to last step in this hierarchy, which is rule learning. Rule learning is hugely important in building models of the world and the primary way that a beginner starts to develop patterns and expectations of their reality. You need to give people opportunities to learn the rules over the course of many instances. And it was helpful for me when I was first learning about incidents and monitoring to have other members of the team constantly vocalizing their actions and the reasoning behind those actions. Repetition gave me the building blocks for discovering patterns in the SRE world. And having rapid feedback and rationale for why the world is the way it is granted me inroads to knowledge. But more than that, this let me be as curious as I wanted to be. I think when information is transparent and available, beginners can really succeed within this hierarchy. So once we've laid the groundwork for scoping our learning paths and conditions for learning, we have to do the actual work of learning. And learning is a lot of work at first. For that, we need to go back to class with some of our least favorite methods of learning, and I'm talking flashcards and tests and other unpleasant things. So I used to think that the path to success in studying was rereading material. And I did pretty well on tests throughout school with this strategy, and I had a ton of confidence going into those tests that I understood the material. But like 6 months later, I realized I didn't actually retain anything. This is what learning science calls the illusion of knowing. In studies conducted by learning scientists, rereading material, or in our jobs going back to the docs repeatedly, has been showed to be largely ineffective at storing something in long-term memory. And storing and linking concepts in long-term memory is necessary for expert intuition. So what do scientists say we should do if we want to embed knowledge in our long-term memory? So their first advice is to test yourself often in low-stakes environments. Low-stakes testing is the frequent use of evaluation instruments over the course of learning something new. Every time there is a word or phrase I don't understand, I write it down on one side of a card and I write an explanation or definition on the other side. And I look at these cards every day and I ask myself to struggle to come up with the answer before I flip it over. I found that over time, this testing reduced my need to relook up information and increased my confidence in knowledge of concepts that I'd learned in the past. So why is this low-stakes testing so effective? It's because in order for our brains to learn, we need to practice retrieval. And retrieval requires a bit of effort. Active retrieval strengthens the neural networks which hold our memories, allowing these memories to be more easily accessed in the future. This is like building a hash map with the neural pathways in your memory. So this is a rule I have for myself. I try to think of a solution for something before I look it up, and that allows me to retain the information better the next time. So while any sort of retrieval practice is useful, it is more beneficial when it is effortful. Why? Because the strain makes those pathways stronger. There are two known ways that we can make learning harder on ourselves, and thus those pathways more resilient. First, we can use delayed retrieval or greater temporal spacing between repetitions. And second, we can interleave our study by alternating between concepts. It benefits me when I'm learning something new to be assigned different types of problems in order to interleave that work. Another tool I use is called the Leitner boxes. So the German scientist Sebastian Leitner developed these boxes. How it works is you take 3 or more boxes of cards, and the cards in box 1s are the ones that you often make mistakes with, and the ones in box 3 contain cards that you know very well. So you look at box 1 cards every day, box 2 every couple of days, and box 3 at the end of the week. And then you promote cards you get correct and demote cards you're getting wrong. This embraces delayed retrieval and interleaving. So I've used this for concepts like HTTP status codes, Linux namespaces, errors I've seen in the past, methods in new programming languages I'm learning, and all of these things made me immensely faster at reacting in a stressful moment like an outage. Even if I didn't completely understand the story of the incident as it was happening, I had enough information to start to debug. So once I had the basics of retrieval down, I wanted to try out more advanced memorization techniques, so I turned to memory palaces. A memory palace is an imaginary location in your mind where you can store mnemonic images. Usually, memory palaces take place somewhere you're already familiar, and you build something bizarre or novel into it, tying these concepts to memorable images. So we can apply this to computer science topics as well. For example, when I was learning about basic networking protocols, I built memory palaces in my living room to remember different aspects of the protocols. I kept this conversation between 2 tarantulas using the tarantula communication protocol to remember different aspects of TCP, for example. Memory palaces are a great bridge from route memorization involved in low-stakes testing to the true powerhouse of expert intuition, which are stories. So this brings us from how we moved from general knowledge we've gained to start building those abstractions of that knowledge into models. So mental models are created in the process of turning patterns and events into abstractions and stories. They are the basis of expert intuition. Casey talked on Monday about how complexity is defined by systems that are too big for one human to understand, and mental models help us make up for that difference. By way of explanation, I want to consider the frilf and goby. Frilf and gobies are my personal mental model mascots. They are these fish that live in rock pools where birds are their biggest predators. And in order to protect themselves, they have this ability to fling their bodies out of water to a nearby rock pool in the event of a bird incident. Although I guess we're calling them bird surprises now. They aren't just jumping on faith, however. When it's high tide, they circle the rock pools from above, and they make these mental maps. Then, in a stressful moment, they jump with astonishing accuracy. The next time the pager goes off at 3 a.m. and a decision needs to be made about switching over regions or making a jump from an attack in your system, mental models are the things that have you prepared. Beyond giving us abstractions and maps of our systems, mental models make us better storytellers, and in turn, more competent in detecting when something in our system doesn't quite match these stories. When we move beyond our experiences with System A and System B to a story about how a healthy system should react and work, we become better at automatically realizing when there is a problem. On Monday, Ryan said this in his talk on learning from success, and I think is absolutely key. Beyond just enhancing our understanding of incidents when they happen, I think they have the power to prevent them in the first place, creating a learning organization. So how do we build mental models as good as the Frilf and Goby? The first step is realizing that mental models are difficult to develop and may take many years of practice. This is because understanding structure is hard. We move from events and patterns to develop structure. And we do this by mentally filing away a massive but finite amount of fundamental knowledge built through experience that can then be used in turn to evaluate an infinite amount of unique scenarios that may impact our systems in the real world. Slowly, through patterns, we build abstraction. I have built all my mental models through observability. And to me, observability is just the idea that everything in your system should be discoverable. My definition of observability comes from the principle of observability in general science. And this is the idea that any input to a system should have an observable output. So for me, observability in this sense goes beyond instrumentation to documentation and historiography. The historical context around why any feature is implemented is an input to your system as much as the data you feed it. Observability makes our systems more hospitable to learners. If I were looking at a new system and wanted to tell how observable it was, I'd ask how long it takes to onboard new engineers. How long would you expect a new engineer to work on this system before they were trusted to go on call for it? So after observability, regular reflection over my first years in operations helped me build out mental models faster. Reflection is critical to sustaining memory and building mental models because it involves several of the cognitive activities that are scientifically proven to lead to stronger learning. Retrieving knowledge, connecting new experiences and new knowledge to existing knowledge, and mentally rehearsing what you might do if the same situation happened again. Researchers at Harvard Business School have conducted studies on the relative impact for different types of learning and discovered that at a certain point there are diminishing marginal returns for additional experience when compared to the benefit of deliberately articulating and codifying your past experience. For this reason, when onboarding to a new system or team, it's great to run incident and project reviews at every opportunity. If you don't completely understand the context of an incident while it's happening, this gives you an excuse to interview engineers involved and to learn their reasons for why certain actions were taken during the incident, concentrating on the how instead of the why, as we've heard from several other talks this week. Along with writing up incident reflection documents, I keep a documentation journal. These practices have helped me make up for what I lack in experience with the system. Furthermore, doing these reports gives me a way and permission to interrogate other people's assumptions without feeling guilty about the questions I feel I need to know the answers to. So I think if there are any managers or leads in the room, designing meetings centering less experienced members of your team's questions in these reviews is a great idea. So once we have good mental models built through observability and reflection, we can improve on these models by extending them into explicit models. While intuitions rely on single mental models, deliberative reasoning calls for us to fully understand multiple models. An example people often cite is learning both an object-oriented and a functional programming language. When one feels they're gaining competency in OOP and wants to deepen their understanding of these concepts like scope or membership, removing them in favor of language attributes in a different system can emphasize their true importance. When we build out multiple mental models, we gain perspectives with different types of systems. And I really like this distinction between singular and explicit models because it really explains why experience is so crucial to deeper and holistic understanding of how systems work. When we can begin to hold competing truths about our models, we are on the way to true expert understanding. So using the tool system at my own understanding works really well for me, but I don't work alone. I work on a team. So how can I leverage my team to support me in learning? So a study from the University of Pennsylvania discusses this term, mnemonic convergence, in trying to understand the implications of highly malleable memories, like the ones that humans have. Our memories are very apt to change. They examine conversations amongst large social networks to talk about how community-wide shared memories are formed. The way that we update our memories through conversations with our teammates is a fundamental factor contributing to the emergence of a collective memory. So one type of collective memory is cultural history. To talk about cultural history, I want to take a quick tangent back into the animal kingdom and talk about elephants. And this is something that I learned from Joseph Heinrich's book on cultural evolution. So in 1993, a severe drought hit Tanzania, and it resulted in the death of 20% of the population of African elephant calves. This population was divided into 3 clans, each of which shared the same territory. Researchers studying the elephants analyzed the survival of the calves and found that families led by older matriarchs suffered fewer deaths during the drought. Furthermore, 2 of the 3 clans unexpectedly left the park during the drought to look for water, and both of those had higher survival rates than the ones that stayed behind. These severe droughts occur only once every 4 to 5 decades, and the last one had hit in the 1960s. It turns out that exactly 1 member of each of the 2 clans who left the park were old enough to recall life in 1960. So elephants have to pass this cultural memory and this mnemonic convergence through experience, but humans have a super special advantage, and that's that we can just tell one another. So think about the worst outage you've ever faced on your team. Are you thinking about it? Are you in a dark place right now? So that incident left a mark on your memory and the memory of your team that someone coming in without those memories doesn't have. The way you monitor and operate your systems is built on top of those memories, and a newcomer to the system may not know why or how it's been built that way. When I first started at BuzzFeed, our team told me the story about Hurricane Sandy and how they had to switch to a cloud provider overnight. This impacted a lot of our design decisions. Some of the infrastructure we still have today was built out of that path and is dependent on it. Knowing this story and having this information makes me better understand the infrastructure than if they hadn't told this to me. Institutional knowledge is hugely important. When a new person joins the team, we need to make sure that they understand that knowledge. So a memory tool within my team that's been essential for helping me grow as an engineer is having and working with a team that has a growth mindset. There's this 2010 study done on 5th graders by the researcher Carol Dweck, where she gives the kids puzzles and then she splits them into 2 groups. When the kids complete the puzzle, she told one of the groups that they completed the puzzle because they were smart, and she told the other group that they completed the puzzle because they worked hard. Then she gave them another harder puzzle. Kids in the group who were told they completed the puzzle because they worked hard did significantly better on the second puzzle. Dweck commented that emphasizing natural intelligence takes it out of the child's control, and it provides no good recipe for responding to failure. We just replace child here with SRE. And I think it makes perfect sense. So learning requires a ton of failure, no matter how smart you are. You are going to come up against problems that stump you. Having a team that believes you can work through these problems is key. So growth mindset is a great foundation for a team to promote healthy learning, but there's one final tool I want to talk about, and that's psychological safety. Psychological safety is a shared belief on a team that you are safe to express yourself and to ask what you may perceive to be naive questions. I hope that through this presentation, I've shown you the benefits of memory to quickly gaining better understanding of your systems, but memory goes beyond your work. Many studies have shown the link between memory and mental health, and that when our mental health suffers, so does our ability to retain those strong ties I talked about between the concepts you're learning and your mind. So on a team, I really think we need to feel that the team and the environment is oriented around solving a problem primarily, and that's what we care about, that we're not a place that cares first and foremost about blame, and that oftentimes outages surface emergent properties about systems, so no root cause. If you're not in a place where you can sustain good mental health and you feel psychologically safe, your memory is going to suffer. And if your memory suffers, I think your team's ability to respond to incidents will as well. So looking back at that first outage and looking at myself now, I don't have a fear of incidents. In fact, or surprises. In fact, they are my favorite part of my job. Optimizing for learning has made me a better engineer, but more than that, it's forced me to look at systems in a way that is very human. So in summary, we can prepare by using constraint satisfaction problems and leaning on hierarchies to learn. We can study by using low-stakes tests, practicing retrieval, delaying and interleaving that retrieval, by using the Lightner boxes, and finally, if you're up for it, building memory palaces. We can abstract by building Frilfin-Gobi level mental models of our systems, by moving from events and patterns to structure, and we need to make sure those events and patterns are observable and complete so we can practice observability and then we can reflect. And we need to experience different types of systems. And we can learn together by embracing the cultural memory that we've created, having a growth mindset on our teams, and building psychologically safe workspaces. I want to thank you all for listening to me talk about learning, one of my biggest passions today. I hope that this pattern of preparing, studying, abstracting, and learning together can benefit you and your organizations in some small way. If you have any questions or want to talk to me more about this, I'm on Slack and Twitter. I'll be around all day. And at this link, you'll find GIFs with a list of resources from this talk. Thank you so much.